And welcome to the second part of the most common misconceptions about design patterns. So, although many people might know me already, the obligatory introduction slide. So my name is Klaus Iglberger, and what I do for a living is indeed, I'm talking about C++. And now, this does not sound particularly entertaining or fun, but it helps. So I do training classes, consulting, all other kinds of things all around C++. All right, so some of you have been here last time. And indeed, last year, I've actually already talked about the same topic. But this was entitled 1 of n. And last year, I talked about different design patterns where we used the terms incorrectly. So I talked about builders, factory method, bridge, and also about the term design patterns itself. This year, I kind of want to continue this story. So again, I want to talk about design patterns, also to some extent about terminology, how to use these terms correctly, but there's another little detail that I want to focus on this year, and that is virtual functions. And yes, you might be aware that in the community, virtual functions do not have are not so popular anymore. So, for instance, CBCon 2022, Vika Bogoselvic talked about the hidden performance price of virtual functions. And so, yeah, of course, all you realize that virtual functions, of course, have a cost associated with them. Of course, yeah, there is a little overhead, both on the memory side, but also on the runtime side. And so, many people talk about how to avoid virtual functions, how to speed up performance. Interestingly, there was also the other point of view. Yeah, just in the year after, Sasha talked about optimizing away virtual functions may be pointless. Pretty much talking about the performance aspect of virtual functions and why it might not be so bad after all. But there is this little battle in the community. Should we use virtual functions? Should we not use them? And so now I'm super proud that I can finally chime in. Yeah, put my opinion on the table. That's going to be fun. And so I'm talking about two things that usually are suggested as replacements or improvements. And so first, I want to talk about CRTP. That's the first part. And second, I want to focus on stud variant a little bit. All right, and so let's dive right into the first beloved cryptic abbreviation, CRTP. So, of course, I know many of you know that, many of you potentially use that, but there might also be a couple of people that are not really familiar with this and are now wondering, what is this cryptic thing? So it's actually something quite old. It's from 1995. So back then, and there wasn't even a C++ standard at that time, yes, it's so old. At that time, James Coplin wrote a paper in which he just described a template-based pattern that he had recognized in several code bases. Yeah, he reports about 3 different examples and occasions. It didn't really have a name for that, but the paper was entitled Curiously Recurring Template Patterns, because for him it was a pretty strange, curious pattern. It was recurring because it occurred in several places, and it was template-based. Okay, obvious title, right? But he did not really give it a name. And so the name of the paper became the name of the pattern, which is weird. Yes, indeed, but okay, so this is what we're living with. So, what is this pattern about? Of course, it's about inheritance. And it's about the big wish to get rid of virtual functions, to get rid of the overhead of virtual functions. So, imagine this, okay, I know, simple but good example about animals and sheeps. Animal being some base class, sheep being the derived class. Then the first thing that CRTP would do is it would make the base class a class template. And then here comes the curious thing immediately. The derived class would, of course, inherit from animal, but would itself provide as a template parameter. Whoa. So, of course, if you've seen this before, you're nodding and say, Klaus, go on, move on. But if you've not seen this before, this truly is curious. And you're thinking, does this even work? But it actually does. At a point, you've written class sheep, you've forward declared the class sheep, kind of, and yes, you're allowed to instantiate templates with incomplete types. So it's perfectly legal, perfectly fine. But now you realize that this template parameter T is indeed the derived class, that type of the derived class. And so one of the things we do in this pattern is we name this template parameter derived. It's like a signal. It's like a thing that people recognize quickly. So, but then animal itself is a base class, but not really a polymorphic base class. And remember, we want to get rid of virtual functions. So definitely one of the first things we do is we make the destructor private. The default constructor could be private too, doesn't really have to be, but why not? Now, of course, the derived class cannot really destroy the base class anymore, but we allow that. So we explicitly befriend the derived class to say, yeah, okay, you're allowed to do that. I know, looks a little weird. Actually, I'll show you that this is a pretty good way to protect yourself against misuse. So it really is part of the pattern nowadays. Okay, but then, just as a comment, you don't have to do anything in the derived class. Yeah, ignore the destructor. Remember the rule of 5. There's nothing to do down here. It's just about the base class. But then the base class, of course, as a good base class does, provides the common interface for, well, all the animals. So my animals now apparently make a sound. But this is not a place where I know what the particular animal does. The derived class knows that. So the derived class would provide the implementation. The derived class would say, for the sheep, or something like this. So this is the interface, this is the implementation. There is no virtual, so how do we get from here to there? Well, we know what we are because of our template parameter. We know we are a derived, and in this particular case, we know we are a sheep. Hence, what we now can do is we can convert ourselves, by means of a static cast, ourselves here, this pointer, to a derived object, which is perfectly legal. We are derived, right? And we can call make sound on that. Pretty curious, but it works perfectly. Perfectly legit. According to language rules, there's no undefined behavior, anything. This is perfectly okay. But this now basically means that we can use a sheep via the base class without having to pay any costs. So if you now write functions by means of animal, or in terms of animal, of any derived animal type, you can call make sound or other functions, but you can't directly work with sheep. There's no virtual function call overhead. The function can even be inlined. And so this runs at peak performance, although you still have the original property of an inheritance hierarchy. So again, if you've seen this before, you're not, Klaus, move on. However, if you've not seen this before, your brain is clicking and thinking, whoa, this is amazing, whoa. And you're believing, well, this is what I need. And of course, immediately you're making big plans. Yeah, next week, of course, after the conference, not tomorrow. Tomorrow is still conference, but next week after the conference, you're going back to your code base and you're replacing every single inheritance hierarchy with CRTP. Yay! Okay, if this is what you're thinking, hold your horses. That's not what you should do, please. And I've seen so many people that actually did that and then rolled it back later. So before we now move on, I should talk about the 2 things that you should definitely know before you replace every inheritance hierarchy with CRTP. So, first thing, if you use this pattern, every derived class has a different base class. And I should actually say this again because it's so important. Every derived class has a different base class. So you do not have this usual property of an inheritance hierarchy that you have a common base class, that you have, say, a vector of animals. It doesn't exist anymore. There is no such thing. Every derived class is different. So, and this means that in many cases you just cannot use this everywhere. It is a little special indeed. But there's one more thing that I feel is potentially even worse. If you now use this, and we have seen this print function before, then, well, of course, this is pretty much how you would write it. You would write a print function for animal of any derived class. Yeah, this is a print function that can deal with sheep, but also later with horses and cows and whatever. It would be a function template. Of course, that's the only reasonable way to use it. But now, let's scale this up a little bit. Yeah, this is these slide were examples. But now let's scale this up to a code base of several 100,000, perhaps million lines of code, where this abstraction is pretty much used, well, everywhere. What this means as a consequence is that, of course, every function that uses this base class, every class, everything is itself a template. And now potentially you're thinking, okay, we have just templates, good for you, but most people in a million lines code base actually want to have a lot of code in the source files, because else compile times are just totally miserable. You do not want to have a million line template header only library. That doesn't sound reasonable. But this is exactly what you might get if you use this pretty much everywhere. And so, now, I think this is a pretty big downside that you should be aware of before you start to use it. But now, this is the 1995 form. Just a couple of years ago, Ben Dean actually gave a pretty good talk, very good talk, it's a Ben Dean talk, at CPBCon 2021, talking about the deducing this pattern. Now, this is kind of the nickname for the feature that today we call explicit object parameters. So he gave an example, which just scale up so that you have, or that you get an impression. So say you have a numerical functions base class. And immediately when you see derived up here, you know, okay, it's a CRTP base class. And this base class provides a scale function, some multiplicator, that uses the underlying object, and here is it again, the static cast, to get a value, do some multiplication, and to set the value. You scale some value. The derived class, called sensitivity in this context, provides get value and set value. So I can use this class from here. And now, in the main function, I can create a sensitivity value, or object, and scale it by means of this base class function. Yeah, nice. So this is pretty much the CRTP pattern, absolutely. But now, Ben was arguing, we don't need this anymore, we can do better. And he is using a C++23 feature, the feature of explicit object parameters. So what is happening here is that we are deducing the type of the this object. So indeed, this is a forwarding reference, or universal reference. So we deduce the type of this object, and because we now know the type, we can call get value and set value automatically. And note, they're not template parameters anymore. It's just regular classes that deduce their own type. This is better, right? This is way less cryptic. It's not template code anymore. So it's just better. Whoa. And so Ben kind of concluded in the talk, so CRTP really just, I guess, goes away. Of course, if you say something in a talk like this, of course, people are reacting. Of course. And consequently, a lot of people picked up the idea and talked about how much better modern C++ code is. So, the shape rectangle example, pretty much the same idea, with deducing this. And also, other talks, I think I counted at least 3. I could only find 2 screenshots, unfortunately. Here, similar thing, animals, cats and dogs. I like sheep better. Okay. And same pattern, right? So now, side remark, which this little thing, I know it's crossed out, but you can read cat, right? Dog inherits from animal cat. Ooh. Undefined behavior. And that's exactly the reason why we make this, this destructor private. Oh, this helps. This could not have happened with a private destructor. Yeah, copy and paste. And of course, I don't blame Timur. This happens. If you create slides, it always happens. But it happened even in real code. Okay, private is good. So, many people picked up on this and said, well, actually, this is not what we use anymore. We now use explicit object parameters. So, and this is now the same example, using sheep again. So, we could implement make sound with, for instance, a reference to const. Why not? Doesn't have to be a forwarding reference. We could call make sound impl, which is now implemented in sheep. In the main function, we could create a sheep, store it as a reference. We could say sheep make sound, and yes, you would hear this beautiful mrrr. And we could also say animal make sound, yeah, calling this via the base class, and this would not compile. It would not work. And surprisingly, this was indeed happening in all of these talks. There was a lot of slides on these talks, on this slide, a lot of code on these slides that would just not compile. Weird. Why do experienced presenters and speakers put things that actually don't work on their slides? Well, I believe it was not so much of a surprise, but to defend Ben in this context, he actually said this right away. So again, I'm just showing this explicitly. So there was this base class, function 1, function 2 being a template, function 2 using explicit object parameters, some derived class that inherits publicly. And then if you have a base called func1, func2, you would, of course, deduce base types. But if you now use derived, you might actually not really get the derived type. You might get the base type of something. And that is exactly how these explicit object parameters work. You actually derive the static type of an object, not the dynamic type. This, however, unfortunately, was missed in a lot of these talks. And so, well, it didn't really work. So there was something else in Ben's talk. There was a link to Jonathan Bucara's blog, Fluent C++, to some blog from 2017. So unfortunately, Jonathan isn't writing anything anymore. Still, I think there are a lot of things that are pretty useful if you look this up. But there was one about CRTP, an entire series about CRTP. And there was a very interesting paragraph in one of these blogs. But there are several ways the CRTP can be useful. Here, I'm presenting the one that I see most in code, adding functionality. And another one that is interesting, but that I don't encounter as often, creating static interfaces. Interesting. 2 forms of CRTP, at least. And I think this is exactly part of what creates the problem. So, you remember this numerical functions example? Numerical functions being some class that contains some code that we kind of inject into sensitivity so that we can use it at this point. So, at this point, we know it's a sensitivity object. And so we can call this. And everything is just fine. Yeah, we can use these explicit object parameters. We deduce the type of the real thing, sensitivity. Everything works because we know what everything is. Good. This is what Jonathan Bucaras was talking about when he said adding functionality. But then there's the other use case. The other use case that I presented before, the animal base class with the deriving sheep, where I actually use everything via the base class, via the interface. If I replace this with explicit object parameters, unfortunately, at this point, I am not able to derive the type of the type of the real thing, the dynamic type. I can just only pick up the static type, the static type being animal. And so there is no make sound impl. It's a compilation error, plain and simple. And so this is what does not work. And so, in summary, yeah, there's just 2 different forms of CRTP. 2 terms, CRTP, that are kind of ambiguous. If I say CRTP to you, you might have thought about one of them. You might not have thought about the other one. And this creates a problem for the industry. And that is why I believe these speakers are just victims of an ambiguous term. Yeah, they hear CRTP, they're thinking about something, say, oh yeah, this works, but it might not. And so, this misunderstanding is something that we should clean up. So what we need is new terms to clearly and properly communicate about what we actually want to do. So, and now first, I have to apologize. Yeah, I have to apologize officially because I missed this opportunity. So you might have heard about this book that I published a couple of years ago, so 2 years ago. Yeah, and in this book I'm actually discussing both forms of CRTP, but I'm actually naming both CRTP. I'm not distinguishing the name, and this is just wrong. So I officially apologize. It's my bad, but today I'm trying to make up for this. I'm suggesting two new terms. So if you truly want to use CRTP for static interfaces, for a base class, then, well, yeah, you provide a base class, a common interface, an interface that everybody knows, that everybody uses, a base class for a related set of types. And you really use it via the base class, the abstraction. And yeah, it is an abstraction, thus a design pattern. And I think I go with Jonathan here. I would say, let's call this static interface. Let's call this static interface to communicate what I need is a compile time relation between types, a family of types. For me, this sounds reasonable. But then second, there's this adding functionality via CRTP. Actually, I think we have had a term for this before. For a long time we've had a term. So in this context, we just provide an implementation detail that we just inject into some derived class. We're never really going to use it via the base class. We might use the functionality, of course, but not via the base class. And so we don't really introduce an abstraction. It's just about inheriting a set of implementation details. And this is which, for decades, I would say, we've called mix-in. Mix-in as a thing that just is an implementation detail. And so I suggest to use these two terms to just make a difference between these two. And so, some guidelines. Prefer to use the term static interface to express the intent to create a static family of types, a template-based compile time family. A static interface is a design pattern. You are creating an abstraction. It's not just an implementation detail. That's something that CRTP itself cannot really do or replace. Or with explicit object parameters, where they cannot replace CRTP. And prefer to use the term mix-in to express the intent to inherit implementation details from a base class, to inject something via the base class. And this is just an implementation detail. And so, this is where explicit object parameters, a feature in itself, in detail, an implementation detail, this is where there are an alternative. This is where you can use them. Good, great. So now, finally, two terms that help to distinguish between these two things. Which kind of means that CRTP is not entirely going away. Well, depending on what you do, what you try to achieve, CRTP might still have a little bit of a use case. But now, once I've said that, of course, at least one of you says, wait a second, Klaus, no. I don't buy that argument. No, I think we are farther than that. Oh, for sure. We have C+20, and we have concepts. So why don't we just do this by means of concepts? Yeah, that should definitely work too. Okay, so let's try that. What I'm going to do is, I don't have a base class, I just have a concept named animal, just as before. And we require that all animals, all t's that are animals, have a make sound function. Then the print function from before doesn't take a base pointer, it just takes any t, any type, but it constrains that type to be an animal, to provide a make sound function which you then actually use. And sheep itself, well, sheep itself is a regular class. There's no template here, there's no base class, no virtual functions also, of course. This provides some implementation. And of course, we cannot print the sheep. That's it, right? So CRTP, after all, is gone. This is better, this is simpler. But no, I'm not convinced. What types can T take? Well, anything that makes a sound, right? Anything. And so I can be printed too. Me too. It is logical to assume that I can be printed too. True. Anything can be printed. And okay, perhaps you're taking the hint. This is duck typing. Now, this is what, for a long time, we have called duck typing. It takes whatever provides a make sound function. This is not a family, a dedicated family that has chosen to be a family. This is what we usually do when we derive from a type. We opt in. We are one of those. We belong. So no, this is not a replacement. However, while we're here, perhaps we can still achieve something that does replace CRTP. So perhaps we can introduce some kind of tag class. Let's call it animal tag. And then we could additionally require that this T not just makes a sound, but derives from animal tag. And then sheep, well, if it wants to be an animal, it has now to inherit from animal tag. Now, of course, I can't be printed anymore. Me neither. And that's logical. Assume that now I'm unprintable as well. Not duck type anymore. These three guys have not inherited from this particular base class, and so now they're out. I can truly only print those types that explicitly opt in. And this is pretty much what CRTP does. This indeed is a replacement for the good old CRTP. But in other words, there's a little more than just a concept. We still need some kind of inheritance. And note, I think it has to be some kind of base class, something that you do explicitly. If you're asking for some nested type or anything else, coincidentally, it could actually happen. Some type could have this property, but a base class is something that doesn't happen accidentally. And so, if you do something like this, I think you may have a replacement for CRTP indeed. And so, in the end, well, CRTP is just an implementation detail as so many other things too. But still, please use the term static interface if you do want to communicate some compile-time relation between types, this family of types, and use the term mix-in if you want to communicate, I just inherit, get in some other form, some implementation detail. This is, I believe, two terms that make this clear, and use CRTP primarily as, this is the technique I'm doing to achieve this or the other goal. Great. And so, that was CRTP. But now, there's a second term that I would like to address, stood variant. Okay, so I assume all of you have a little bit of a background of stood variant. Okay, but now it's kind of old already, C+17. It's one of the types that you just use. And so let me demonstrate this by means of a little example. Okay, you might have seen talks of me before. I'm an animal of habit. I'm using the same example that I'm always using. I apologize for those that feel a little bored by now, but okay, I think it's still a reasonable example. Again, I'm using drawing shapes. Okay, I know, drawing shapes is not particularly entertaining, but at least this is colorful, right? And there's one silver lining. But let's add some requirements. I would like to add new types, different types, rectangles, ellipses perhaps. And so, first, I want this entire system to be extensible by new types, shape types. Second, let's assume that this must work in many, many lines of code. So let's just say 10 million lines of code. That should work. And say this is something that 100 developers will work on. At least, in other words, it's supposed to be a big project. All right. So let's take a look at some example code. Let's start here. Let's say we have some shape base class. with a nice virtual destructor and a pure virtual even draw function. Okay, it's a simple example. So of course, there are other virtual functions, potentially many more. And of course, draw might take parameters. Everything could be a little more complicated, but let's consider that. Derived classes, circles, squares, etc., they inherit from shape, but now have a task to do. And they have to implement draw. It's not optional. They have to implement draw. It's a pure virtual function. But the poor little circle actually doesn't really want to implement draw. Reason is, this would create coupling. The circle does not want to know about OpenGL, about 3DX, about any graphics library. It just wants to be totally oblivious of this fact. And this is good. After all, this is what the single responsibility principle advises us to do. So, the circle would just externalize this implementation detail. And by means of a strategy base class. Let's call this draw strategy. It's templated on some concrete shape type. That might be circle or square, etc. And this is the point where I now introduce some abstract function draw for a concrete shape. Now, circle has now injected one of those in its constructor. So the circle takes everything circles need, like radius, blah, blah, but it also takes a draw strategy, moves it into the data member, and from now on, the circle knows exactly how to draw itself. It just has to delegate. Nice. Okay, without big surprise, all the other shapes do the same. There is a square too, so that the circle is not so alone, but imagine there are plenty of other shapes, rectangles, ellipses, star shapes, whatever you like. All right, now we have a real base class. And so, of course, we use the opportunity to actually have an entire vector of shapes. Shape pointers, of course, unique pointers of shape. And as something more, we also introduce a shapes factory. Ooh. Okay, there's usually two kinds of people now. Either the people who say, whoa, a factory, or the people, oh, a factory. There's hardly anything in between, but now, in our example, we have a factory. This factory creates an entire vector of shapes. This is the shapes type here, based on whatever is inside this file. Good. Then we also can draw all the shapes. This is just a simple for loop that draws all the shapes. And then we can combine these. Create and draw shapes takes a factory, takes a file name, uses this factory to create shapes, and then we draw them all. Good. All right, and with all of this in place, I think it's time to actually think about details, like how do we actually want to draw? So this is what the OpenGL drawer now can do. It implements the draw function for circles and squares, and well, it uses OpenGL as the name suggests. That could be any other library too. We could have multiple of these drawer classes. And then, of course, we could now also implement the shapes factory. A lot of code, you do not have to read everything, definitely not. But we would traverse the entire file, we'd check out all the circles and squares and create them. And of course, we would make unique all these things, make unique circle, make unique OpenGL drawer, and then put them into a vector of shapes. And in the end, we just return all of these shapes properly configured and ready to be used. Okay, and then, last but not least, we just use this. Yeah, I have a factory, I pass this to create and draw shapes, some file, and here we go. Great. And this works, right? This works fantastically. Well, let's take a look at a couple of details. After all, there's a reason why we want to extend the code. We want to work together, right? You want to do your stuff, I want to do my stuff. And so, therefore, let's just separate work. Okay, so let's introduce what I would call an architectural boundary. So the architectural boundary, above this is what I call the high level, stable code, lower dependencies, and below that is more implementation details, at the low level of this architecture. Okay, and I'm seeing you're looking confused. Okay, forget it. Let's just call this my code and your code. That's way simpler. I have written this part and you have written the lower part. So you take care of the details like how to draw and how to extract stuff from files. I just use this in an abstract form. Okay. Now you, of course, you are able to write new things. You can introduce a rectangle. Now, again, you don't have to read all of this code, but again, this rectangle would take a draw strategy so that it does not have to deal with the details. The draw function would then finally use that, and of course, we would have the according data member to store this drawer. Good. You could also easily just add the functionality to draw. Your OpenGL drawer could now deal with rectangles easily. You just implement the draw function coming from that base class. And last but not least, you could also extend this factory accordingly. Okay, a new else if branch. If it's a rectangle, you do all of this stuff to add a new rectangle to this vector of shapes. Again, with a couple of make unique calls, but else this will work. And so, great. We can work together. You can do your stuff. I can do my stuff. Hooray, right? Great stuff. Okay, I totally admit this is not the reaction I anticipated. I know it's the after lunch session, but even for after lunch, it's surprisingly calm. Yeah, okay. I was afraid of that. I was totally afraid of that. Some of you are totally unhappy about this style of programming, right? Yes, of course. And of course, you also have a name for that. And this name kind of goes back to this book, which most of you know. Again, a lot of nods. Design patterns, elements of reusable object-oriented software. The book on design patterns, I would argue, this is what you call the Gang of Four book. Gang of Four because of these four authors. And the style that you've just seen, this is what we commonly know as the GOF style, the Gang of Four style. Where inheritance and virtual functions pretty much are the answer to solve problems. And yes, I know. This is what is used a lot out there. But you are, since you're here at the conference, aware that indeed there's people that argue apparently against that. So for instance, you might be aware of this title here. The title from a talk from 2013. It was the Going Native conference, which actually was the predecessor, I believe, of CPVCon. So Jean Perrin talks about inheritance is the base class of Evo. Which, if you have not seen the title before, is a funny title. It really is. Clever choice of words, but the content was not supposed to be funny. No. In this talk, he openly complains about all the disadvantages that you buy in when using inheritance. The performance disadvantages, the coupling that base classes create, and there's a lot of coupling going on. The pointers and references that fall out of that. Dangling pointers, null pointers, and lifetime management issues in total. There's a lot of problems. So potentially this is what you were thinking about. So what could you do? And well, there are suggestions. For instance, people are suggesting that there is a way to eliminate virtual functions. I know it sounds a little aggressive, eliminate virtual functions, it sounds like hunting them down, but indeed, there are suggestions to just get rid of them. And here is something that I received as a review for one of my talks that I submitted. I actually don't remember which talk it was, but it definitely mentioned design patterns somewhere in the abstract. This alone was enough to convince people to give this review. I believe that object-oriented programming, and especially its theory, is overestimated. C++ always had templates, and now also stood variant, which makes most of the use of inheritance unnecessary. And now, of course, you not say, well, yes, stood variant. Great suggestion. This might make things so much cleaner, so much nicer. And indeed, you're right. Let me show you. So let's take the code from before. Let's just refactor it by means of stood variant. So first, we start with the circle class. We start with circle. There's no shape base class anymore, not necessary, I got rid of that. So there's just a circle. It's also just a square. And yes, in both cases, you've realized there's no base class, no inheritance. Because of that, consequently, there's also no draw operation. There's no draw. You don't need a draw because this will be added later by means of the variant code. Nice. So this very nicely decouples. You will also realize that there is no base pointers. Therefore, there is no lifetime management, unique pointers, etc. And yes, of course, there's also less code to write. A lot less, I would argue. Nice. This is a good start. Then, stood variant. We now introduced stood variant as an abstraction for different kinds of shapes. I've only two, of course, I know, but there could be more. So stood variant could store either a circle or a square, or potentially, of course, other kinds of shapes. And as such, it is an abstraction. That's why I now call it shape, which really indicates this is now kind of a replacement of the base class we previously used. But then, yeah, what I just said. But then, this is beautiful, isn't it? Whoa! We have a vector of shape values. There's no vector of pointers anymore, but it's values. And it's so natural, it's so intuitive. What is many shapes? Well, it's a vector of shape objects. It's a plural, without any complication, without any indirection. Nice. Okay, still, I want a shape factory. But again, no base class, no inheritance. It's just a class that, in its create function, takes a file name and then extracts all kinds of shapes, again, circles, squares, and returns a vector of shapes, meaning a vector of variants. Okay, also note, this might be super interesting for people that work in embedded, that cannot use dynamic memory, we just create variant values, so there is no need to dynamic memory at this point. No make unique, just create circles or squares or other shapes. Good. And then, whoa, hooray, one other opportunity to get rid of a base pointer, a variant of different factories. There's only one at this point, but another abstraction. Nice. Okay, then, OpenGL drawer. The class from before, the class that knows how to draw by means of OpenGL. But again, no base class necessary, no virtual functions. It's just a class that contains and encapsulates the details how to use OpenGL, with all the data that we need for that purpose. And then again, there's another great opportunity to do some abstraction, a variant of OpenGL drawer. Great. See, it's so much cleaner. Okay, still, I would like to draw all shapes. That's again the for loop. But there's no virtual function anymore. This is now where I use did_visit. And this line, whoa, you might not have realized this before, but this is possible. This line does multi-dispatch. So I call visit with some operation, 2 parameters, pass 2 variants, some drawer, meaning a variant of draw object, some shape, variant of shapes, whatever. And yes, I get multi-dispatch to call the right operation on the right kind of type. Amazing, right? Beautiful, simple. Okay, then we have create and draw shapes. This is the thing that takes a factory, some file name, but also some drawing now because I want to draw all shapes. And in the main function, just put all of this stuff together. Whoa. So, okay, this is the point where I actually did expect some happy faces. It's so much better, isn't it? So much better. There's no inheritance everywhere, anywhere. It's a very functional approach, actually. We don't have any pointers, not even smart pointers. Yeah, and no, I'm not against smart pointers. No, but values are so much simpler, so much more reliable. I have a proper management of graphics code. I mentioned this. It's nicely and properly encapsulated in one place. Very automatic and elegant lifetime management in the sense of I don't need the unique pointers. I just have objects that are destroyed whenever they have to be. and it's less code to write, for sure. I would also argue it's so much simpler. Now, of course, you might say, well, I'm not quite certain, but please do not confuse simplicity and unfamiliarity. I think if you've never seen this before, it may be unfamiliar, then you might not be immediately arguing this is simple. But once you try that, I think all of you will agree this is simpler. And it may be even faster. Okay, now I've done one other thing that you should not do out of habit in a C++ talk. I've measurement fast, and so implicitly performance. This is dangerous. Yeah, in a room full of C++ experts where everybody is looking for performance and fast. Whew. So, of course, now you're expecting results. You're expecting some data, some numbers. Okay, I'll give you some numbers. But I know that this is kind of customary. Afterwards, people are complaining about these numbers. Yeah, it always happens. And if you don't complain immediately, then later you complain on YouTube. So, I'm going to show numbers, but only under one condition. You promise me that you're not going to complain about the performance numbers. So, do you promise that? Okay, I think I've seen most hands, so should be less work than usual. Okay, so, sorry. Good, so here we go. Quick summary of what I'm trying to do here. I have 6 different kinds of shapes, circles, squares, but for others. And do not expect that I took a lot of time to implement very difficult or general hexagons. It's an equal-sided hexagon and pentagon too. I create 10,000 random shapes, and I perform 25,000 simple operations. I'm moving the center point, which has a big advantage because it's the same operation for every type. So this makes the random generation, it doesn't really matter which type it is, it should get the same runtime in the end, which is good. And so really, I can really use a little bit of random to make it more difficult for the compiler. Then, yeah, it's not the newest compilers anymore, but reasonably up to date, I believe. And this is the machine I use this with. So here are the numbers on my machine, my system, my compiler, etc. Yeah, you will not get the same numbers. The classic form that I've just shown before, that's pretty much the result I got. And now also please don't make it a race between GCC and Clang. It doesn't matter at all. So this is the classic OOP result. If I use the variant, oh yeah, much better. For some reason the Clang version was not super great, but if I used an mPark implementation, this was great also. And now, of course, if you see that difference, whoa, much better. It's pretty much half of the time from before. That's amazing. This is where you should celebrate. This is where you should say, whoa, if I now use this, if I replace in my inheritance hierarchies with variant, I'm gonna be the hero of my company. Everything runs so much faster, right? Great, amazing. Okay, but hold the thought again. Yeah, do not immediately plan for next week. Let's first do a little architecture again. Again, we want to separate codes. You have some work to do, I have some work to do. So again, I want to draw a line. So now I have to start somewhere. Say, this is my function. I want to create and draw, but I don't really want to know what I do. I want to use the abstraction. And that's my function too. Okay, so perhaps this is the right point, the right function to, the right place to just introduce an architectural boundary. Good. Again, my code, your code. Okay, it's a little awkward at this point though, because your code only contains the main function. That's not enough. So, of course, your responsibility is to deal with the implementation details of how to draw. So, the OpenGL drawer, that's your code. So, let's just move it down. Good. All right. But okay, sorry, wait. Drawer is what I'm using in my code. Okay. So, okay, this is an error on my side. Probably this is still mine. This is yours. So let's move this up again. Okay. But wait, oh no. The OpenGL drawer is your code. Now, if it's in my code again. So, if you now see this, what you should realize is sometimes there's a lot of coupling happening. A lot of coupling. The variant does not abstract from the types, it actually reveals them quite openly. It's in the code. And so, actually, there is no possibility that we just separate codes. Not anymore. So, what you see here is pretty much an architectural disaster, a total failure from an architectural point. And you just say plainly, there is no architecture. There is no place where you cannot separate concerns. Everything is coupled, everything belongs together. That's not an architecture. So, but then, of course, there was a little more to that feedback comment. C++ always had templates. Of course. If you use a variant, we also need to use a couple more templates, right? Okay, back to the drawing board. Let's just update the things that I need by means of templates. So, draw all shapes is now a function template. Takes a vector of shapes, whatever. I just know they are variants, apparently. And I also have a create and draw shapes function templated at this point. Great. And now, believe it or not, actually now this works well. Okay, this is what I just said, my animations. So, the variant abstraction now is in your code. I don't need to know this anymore. This is truly what you now decide. You decide how many shapes you put inside. And this means you can, if you want to, okay, the other code, you can introduce rectangles. Why not? Now, you can introduce any kind of type that you're not looking for. And you can, of course, extend this, this abstraction in any way you want. Variants, rectangles, ellipses, etc., etc. Okay. You can also easily add anything to your implementations of this factory. Now you extract rectangles in whatever way you see fit. And you can also easily extend the OpenGL drawer. Great. That's pretty much what you need and want to do. And I can, again, put all of these together. So it works. It works. If you introduce some templates. If you introduce some dependency inversion again. But then again, if you do this, if you use now this form everywhere, and use these variants always in function templates, in a 10 million lines code base, what do we end up with? Exactly, a template-only, header-only library, essentially. And again, we're at a point where we probably might not be happy for a long time. I'm sorry. So in the end, I'm very skeptical that this truly is the approach. It just does not work. So, a standard variant is not a replacement for virtual functions. It really is not. What it is it's the antipode of virtual functions, the opposite. It's at the other end of the design spectrum. And so, to just quickly summarize that, variant and virtual functions, by the way, both are dynamic polymorphism. At runtime, we really know what's inside. But the variant is about functional programming, whereas virtual functions are object-oriented programming. And why this now might look or sound like a small detail, but it's exactly the opposite set of advantages and disadvantages. In a functional program context, you have a fixed set of types, but it can easily add operations. In an OO context, however, you have an open set of types on a closed set of operations. It's the opposite. So, from that, I would say, first of all, again, as a guideline, standard variant is definitely not a replacement for virtual functions. But it most definitely is a good re-implementation of what we used to call the visitor design pattern. So, back to this. CRTP and variant. Now, both apparently are not really a replacement for virtual functions. And why is that? Well, because design patterns represent some dependency structure. If you design something, if you choose a solution, some abstraction, there's always some dependency structure associated with that. As a consequence, this means that pretty much design patterns themselves have these architectural properties. So you cannot simply switch or replace one design pattern with another one. That doesn't just work. And so, if you do design software, what you should do, what I think is absolutely vital to have the right solution, is that you should think about designing the architecture first before thinking how to implement them. And based on that realization, which architecture, which design do you want to have, you start to choose, you only consider the patterns that actually fit, and based on that, you choose implementation details. And I don't think that it's really reasonable for long-term maintainability to design just based on performance. I know it's important, but once again, both CRTP and standard variant are just not replacements for virtual functions. And so, ultimately, architecture and design first. So, thank you very much.